Consider two hypothetical investments, Stock A and Stock B. Both present an identical 10% average annual return over the last 5 years. This chart shows the path to that 10%. Stock A is a steady, flat line. Stock B is a series of extreme oscillations, swinging between 30% gains and 10% losses. The average suggests these stocks are the same. In reality, the volatility of Stock B means your actual wealth could look very different depending on exactly when you need to withdraw your money. To measure this difference, we use dispersion, or Al-Tashatat. This is the mathematical study of how data points are spread out from their center. Today, we will walk through the specific calculations for range, variance, and standard deviation to see how they quantify this spread. You can follow these steps manually. You will need a piece of paper, a basic calculator, and a blank 3-column table. Averages provide a center point, but measuring dispersion provides the context necessary to understand the risks hidden within that center. We'll start with a small data set, 4, 6, 8, 10, and 12. Identify the highest number, 12, and subtract the lowest number, 4. The result is 8. This is the range, or Almada. This number line shows it is simply the total width of the data from end to end. The range is easy to calculate, but it only looks at the two most extreme points. If just one of these numbers changed to a massive outlier, the range would expand, even if the rest of the data stayed exactly the same. Because it ignores the distribution of the numbers in the middle, we need a more detailed way to measure how every single point contributes to the spread. Let's use a new dataset for our main calculation, 2, 4, 4, 4, 5, 5, 7, and 9. First, we find the baseline average. Add these 8 numbers together to get 40, then divide by the total count of 8. This gives us a mean of 5. You can write mean equals 5 at the top of your paper. Place our 8 raw numbers into the first column. In column 2, record the distance from our mean of 5. First row, 2 minus 5 equals -3. The rest of the column shows a mix of positive and negative distances. If we try to sum this column now, the negative and positive values simply cancel each other out. -3 plus 3 is 0. -1 plus 1 is 0. The total sum is exactly 0. To find the total distance of the group, we need a way to make these values positive while keeping their relative proportions intact. We can resolve this by squaring every value. In mathematics, multiplying any number by itself, including a negative, results in a positive. Fill out your third column by squaring the numbers from column 2. Our -3 becomes a positive 9. Now, when we sum this third column, the total is 32. To find the average of these squared distances, we divide the sum of 32 by our total count of 8. This result is 4. This metric is known as the variance, or Al-Tabayun. The variance is expressed in squared units. To return to the original scale of our data, we only have one more step. Take the square root of the variance. The square root of 4 is 2. This is the standard deviation, or Al-Inhiraf al-Mayati. We have now calculated a single number that accounts for the distance of every point in the set from the center. You have now built a full dispersion map for this data set. This number 2 functions as a statistical ruler. It tells us the typical distance a data point sits from our mean of 5. When we apply this ruler to a bell curve, we see how the data clusters. By moving one standard deviation, 2 units, to the left and right of our mean, we define the area between 3 and 7. In many common data distributions, about 68% of all points will fall within this one standard deviation range. It shows us where the normal or expected values live. To practice this yourself, look at the weather data in the video description. Try to calculate the standard deviation for the temperatures in 2 different cities to see which one has the more predictable climate. Understanding these metrics allows you to look past a single average and see the full spread of the numbers, turning this simple summary into a detailed map of the data's behavior.